Okay. Hello, everyone. I hope everyone can hear me. Okay. If no, please let me know in the chat. I will fix it. Okay. My name is Andrey, and I'm a software engineer. I'm working in experimentation at Meta. It has happened that every several years I change my domain area, and I have to learn a new area almost from scratch. The same has happened with A/B experimentation or testing not long ago. Eventually, it appeared that this wasn't so easy to understand what the A/B testing is from inside, especially the statistics part when your university is long gone. Of course, there are plenty of courses outside, but I felt that they're skipping what the most they think are very basic. There are some rules that have to be taken as given unless you want to go through the full course of math. But for me, it was not so explicit. As I already passed this way, want to share it with you. Maybe you will be able to learn cover this gap a bit faster than I did. I consider that software engineers is the major audience for today. Because it's not because I just like software engineers, because I think it's just because my examples and the level of knowledge is most close to this group. And yeah, if you have some statistics background, it might be too easy for you. It's definitely will be too easy for you. And yeah, so please welcome. Small important notes on the format for today. That will be no Q&A at the end. I'm really sorry. This is just a company policy. I can't do this. But I leave my email at the end of presentation, and I'm happy to answer it through the email. This session will be recorded and will be available in several days. So no need to write down all I will be speaking about. And yeah, let's begin. So what our agenda for today? Today we will go through the story of one experiment, which is a very basic experiment, of course, and what we get from the just introducing of this experiment to a metric-based decision for this experiment. And while we go through this in our way, we will go through how to measure, how to build a trust to your measurements, and how to compare your results. So it's like essential parts for any experiment. During this presentation, I will introduce a bunch of terms, technical terms. I will try to visualize and simplify them as much as possible, but essentially they're essential, so I can't skip them. But I will highlight you with this one. So I think the basic knowledge, if you know what the probability is and how to convert it from ratio to percentage, it should be pretty enough for today. And let's start with measuring. And measuring block, of course. So first of all, a bit of boring stuff. Let's start from the wikis, what the A/B testing is. So A/B testing stands for user experience research methodology, which consists of randomized experiment that usually include two variants, A and B. Yes, I read this definition many times, and I spent a lot of time before I deeply can understand this. And actually, it's impossible without special techniques which will be introduced. So let's go and try to make it a bit simpler what this phrase actually means. By this phrase, actually, for our programmer example, let's take this one. Here's the definition. We have two versions of, for instance, our website. Very simplistic website, just with some random text, couple buttons, and that's it. For instance, we have our original site, which shows green button, more. And we want to introduce a new version of our site with a red button. And it will be our new look. And this will be our test version in this case. There's one more very essential part for this. Our users. When we do experiments like this, we want to compare something, the users must be randomized. We can't choose users on any attributes, on any data we know about our users. So they must be completely random. So because we are talking about statisticians part, let's just assume we have some router which can randomly split our users between all the current versions of our site and new versions of our site. So just green and red. If I just in case miss user block in my presentation, because yeah, it's moving around, just be sure that there's always present. Just maybe I just forgot to update the picture. Okay, if we have this setup, what the simplest we can compute, what metric, simplest metric we can compute to see the difference. Let's count some numbers from just out of our users and what we actually changed. Clicks on our more button. This how it can look if we get to the numbers. Let's get so users come and see our site, and some of them click on this more button, and some of them don't. If we collect just numbers of how many times they saw our site, just open the form, and how many of them clicked, we can get some data out of it. So, for instance, we started collecting this data and we fixed some time, and because our system split them by half, we expect, okay, finally we collected 1,000 clicks on, or 1,000 views on our old site and 1,000 views on new site. And because we also collected how many clicks we have on each version, we see, okay, for instance, just for example, somebody for old version clicked 600 times and for new version clicked 700 times. Yeah, after that, we can build some ratio from the very basics of statistics, just divide one to another and get, okay, probability of clicking to the more button is just 60% for old site and 70% for new site. And actually, here, this is our first metric. And yeah, it might be not so obvious from the beginning, but actually, this ratio is industry called click-through rate, or CTR. Yeah, because it's just 3 words, it might be too long to pronounce them. So CTR is exactly the ratio of users which view our site or ad or anything else we are interested in, and the users who engage to the next step, like click through to the next level. In our case, it's just a more button. Despite of this simplicity, it is pretty powerful metric and which can be used in different scenarios. Also, there are many flavors based on this idea, which just adding more constraints when counting. For instance, if we assume that users we want to collect must be unique, this metric will be called click-through probability. And it is a bit different metric, and it's harder to collect and so on. We don't need it for today. I just want to make some hint that it is pretty, there's a lot of variance of these metrics. Okay, how we can apply this click-through rate in real life and in real examples? Just some ideas. We can, for instance, there's let me start from the what constraints we have in real life. This idea is good for similar experience when we want to test pretty similar experience between each other. The events must be pretty frequent, so we can count it big numbers and not count it just single numbers. And action must have clear correlation between each other. So yeah, in the pros example, it's nice, can be counted when we want to compare cats and dogs, 50 hundreds of shades of gray, and so on. But if you go to the more longer scenarios or different experience, it will be a problem for A/B testing. Actually, not just for one single metric, just a general problem for the A/B testing. So okay, that's if you have this general idea. Let's formalize also some thoughts of how we do A/B testing. So every A/B testing driven by hypothesis. And for the hypothesis, I mean that we must establish clear correlation or clear understanding of what we want to test and how these events are connected to each other. For instance, okay, here's our side. Let's say, can we say something like changing of color of more button from green to red will increase login rate? Yeah, there's one more button. And yeah, it's not working like this. It's not possible. Oh, sorry. Yeah, like this. Yes, so these events are not tightly correlated between each other. So you can't say that, okay, we change one button and we'll look how we click to another one. It's not so straightforward. But yeah, testing of this essential button and visiting next, yeah, will be a pretty good hypothesis. To generalize of the idea of hypothesis, there's just a general phrase which is pretty helpful when you try to emphasize what you want to do. So in general, what change from which initial state will lead to what result? And in this case, it will be this scenario. Result in change are connected. Sorry, oops. Something with my light. And that was pretty basic start of our first metric. But is it actually enough to say, okay, we see better CTR on the red button? Yeah, for the first time, maybe that's okay. But will this result be repeatable, reproducible every time? And here it comes our trust. For example, I have my red and green button test. What's next? Can I trust? But how many users should click on this button or view my site so I can trust the result? It will be repeating every time. So here things become tricky and start converting from simple numbers into statistics. And for that, we will get to our statistical part. Actually, trust split into two parts of majority of this, split into two parts. First of all, are these results stable? Will they reproduce each time I run my test? And in that case, we will try, and we will do it today, to define what is true probability of our metric. And second part is about the size of our experiment. How many views I need to see, need to get in order to trust that the group is big enough to be representative. So it is about experiment power, and if it happens, I don't know for now. I will share this in second part of this talk someday, maybe. Unfortunately, it's too much for just 1 hour. Okay. For the next part, let's try to establish what is true probability. Actually, it is true probability means the one which is most likely we can observe in our scenario. This example usually done through coin flips. So let's switch to coin flips for now. I don't want to break this tradition. It might be just easy because coins usually have a probability of half and a half, 50% for heads and 50% for tails. For instance, we have a coin. It is a usual coin, and we have equal chances to get heads and tails. Let's flip this coin 100 times to get some statistics on how many heads and tails, and repeat this test 10 times. Then we get a scale of probability, and we quantify our results for like each 10%, and put how many like our probability from each of these 10 experiments on the scale. We will get something similar that you see right now on top of the slide. So it will be the most likely you will see majority on the middle. For instance, we are looking for tails or for heads. It's not much difference here, and the majority will be in the middle, and you will see some numbers on the left and the right. Then let's repeat this trick and make it 100 times. You will see pretty similar number picture. We can quantify it a bit more in more details, not just by 10%, but by 5% scale. And we will see the still peak in the middle. And this distribution, which we see right now, is called binomial distribution, which means we get our results and we form some shape of our probabilities, which is most likely can be on this coin. In case of this, we have some screwed coin, which is like don't have a 50% chance of heads, or maybe for 70% of heads. This probability will move to the right or to the left. But what is important for now is that it is forming this shape that in the middle you see the highest peak, and it is going down after that. It means that it has some convergence around the particular number, and you don't need to recompute it every time. We just need to prove that with a particular, for instance, coin, or for some event, for some scenario, you can establish some kind of area of most likely probability. There's some limits, of course, for this situation, similar to what was with the site. Event must be independent, and the event must have two outcomes, only two outcomes, like heads and tails. And of course, each event must have a same probability every time. So if we flip in the same coin, it's okay. If we show on the same side, it's okay. So yeah, we can convert it to site, but it's not so important in this case. Now let's get to the important part of statistics: why we need this binomial distribution. Yeah, so I see the question. So I think it is too far for today. Yeah, it's just a very basic. It is about bootstrapping, yes, for sure, but I won't touch it today. So yeah, binomial distribution is important. That if we look at the picture on the left, and we go to the more and more quantification, will form a smooth curve. And with approximation, we can convert it into normal or Gaussian distribution. So this is just a curve. And so yeah, blue is binomial, black is normal. Why it is so important that we get to normal distribution? This is because normal distribution has some additional features which are not included into binomial. We can't use them just from binomial. For me, it wasn't so clear when I just learned this course, and I think it was some one of the tricks. So the normal distribution has two very important parameters that we can use in the future. So first of all, if we run just one single test, we know that mean of this will be our expected probability in the middle. It will have the mean is our what we can in this case call true probability. And the second part is the standard deviation. Standard deviation is just a standard measure of how wide this distribution will be, and just a general formula that okay, for one standard deviation it will include 68.3% under the curve, so it's about integrals, and the two standard deviation will have about 95.5% and 90. It's these numbers are pretty magical for I think the, software engineers. So yes, you need just to maybe remember them if you want to use it for some reason, but it's not so common. But this is just how it is. So standard deviation in the case of normal distribution has a formula which can be computed from mean probability and number of samples. In our case, number of views of our site. And you don't need to remember this formula. I will show it many times, and you can easily Google it later. And here it is. So this is how our distribution will look like. Let's go to the special case. So standard normal distribution. So normal, just common normal distribution is good, but we need a way how to normalize this distribution from different scales. So we need the ability to compare different scales, different results. And for that case, if we take the special case of distribution from which has a mean at 0 and standard deviation of 1, we can build what is called standard normal distribution. It's also called the Z distribution. In this case, it can give us ability to convert from our results into some standard normalized results and compare between different groups. For the comparison, there's a special Z-score table. Yeah, it's completely available. Just a static numbers, a set of static numbers, which can be used to convert our results to standard deviation, to standardize the results. So here also we can why it's important. So we in general we want to compute the area under the curve with some fixed percentage. In industry, its most frequent usage is 95% of confidence. In this case, yes, I call it confidence. So the confidence is what is under this curve, the area under this curve. So in this case, yeah, we have our probability, we have our standard deviation. It is essentially the same as standard error in many scenarios that is used. And if we multiply our standard deviation to Z-score of at the particular confidence level, we will get what is called margin of error. And to make it more visual, yeah, this margin of error is built in a confidence interval. So this is it is also called CI. For instance, this picture is about 95% of confidence level interval. And for instance, I just take this interval out of previous coin flips. And in this case, we can say that in 95% of chances with confidence, we can say that our coin will show the results are from 30% to 70% to show heads. On the right and on the left, this is tails, which is about 2.5%, which is the potential error which can happen. And yeah, in our case, Z-score for 2.5%, 2.5%, it will be it is always 1.96. It is just a constant number, and it is used in many cases. Yeah, let's update our example with this new knowledge and show what's important for this. So I just imply formulas in the picture. So from the CTR and number of views, we can compute standard error, and it will show us something like some numbers. And I don't focus because it's not so important right now, but yeah, you can apply the formula. After that, you can multiply this result with a standard error and get your margin of error, essentially the bar of the confidence interval. So I showed specifically on the different bars. So in our case, we see that these intervals are not overlapping. They're highly different. And it means with a high confidence, we can say that there's a difference in our experience. And it's pretty natural to say that, okay, red button is better than green button. That's cool. So we, in this case, we not just show the difference between two data points. We show it with the area of high confidence that this change will be pretty consistent. But okay, for instance, you want to see smaller changes, or you want to read more metrics. How you read this overlaps in case of this difference is much smaller. For instance, here we had a difference of confidence interval around 3% in each direction. And just in case we moved our experience just on 2% or 1.5. For that case, it's not clear. Yeah, what to say if we see some overlaps like this, like on the left, or how to, even if we know how to read it, what to do with intervals on the right if you see a lot of metrics. I mean, you can read it, but potentially, but it's very slow. How to make it fast. And here's the last section of for today's presentation is making results comparable. The last major term for today will be statistical significance. But yeah, I have to introduce several more minor terms on the way to get to it. I think it might be the hardest part for today, so please don't try to remember formulas, and yeah, they can be Googled easily. First of all, I want to introduce null and alternative hypothesis. What does it mean? Hypotheses are about statements, and let's do some logic, not just numbers or statistics. So null hypothesis, or H0, or it's also called like our initial statement, is that probability for green button and red button are equal. And with the help of some equations, how we can solve it. So let's write it that both probabilities will be shown on the left. So that, okay, difference between one and another probability is equal to 0. In that case, alternative hypothesis, or HA, is about that these probabilities are not equal, and essentially that probability of red and probability of green are not equal. So if you move to the left, so they one minus another is not 0. This difference is essentially give us the name of the statistical significance. So we can this gives us exchange two outcomes. First of all, rejecting null hypothesis means that we are getting our results as statistically significant. And moving both probabilities to the left from 0 give us ability to get to the differential scale, which is much easier to read in case we have more metrics, and I will show why in just in a moment. So yeah, because we can just subtract them. Because we decided that we can subtract them, we need to establish some combined confidence interval around this subtraction. Actually, it can be done pretty easily just by summing data from both versions, and it's usually called pooled results. Pooled means combined, and let's compute pooled standard error. So combination can be not just from two versions; it can be more versions than two. The idea is still the same. So it is pretty same formula of probability, but instead of just comparing two numbers, let's just sum clicks and some views on both at the same time. And in that case, we get our average probability. With this one, so we have out of this, according to the same formula, we can get our standard error just using sum of clicks and margin of error. It will be out of this data. And in this case, you can see that we are changing our scale from absolute scale to differential scale. What is nice, so you don't, of course, it is just an internal assumption that I moved from subtract probability from the right experiment and from the green one. So we put a difference and put a confidence interval of this difference, and it's all around 0. And this 0 is not some kind of confidence interval. It is just fixed 0. So all the confidence interval move to the one side to the right. And that's it. Also, it gives us one more benefit. Our confidence interval becomes a bit smaller. Before it was around 3%, and now it is 2%. It might be not so important for this picture, but if we go to something bigger, actually it improves our confidence interval, make it smaller by 30%, and it is really important when you want to measure some smalls. So yeah, that's a good question. What's the difference between absolute and differential scale? So the difference is that when we before we get to statistical significance, so we started we tried to compare just the probabilities on both sides of equation. And now we move them both to one side of this equation, which gives the ability to show changes, not just from what it was before to some new value, but all changes can will start out from 0, and like your starting point is always around 0, and you see how you move your change from this 0 to some percentage. You don't need to know where it was before and where it is now. You can just see, okay, I moved it in some direction. And also, it becomes much more comparable. Yeah, exactly. So I will show you how it will look like in our side. So if you remember before this computation, it was two computations of on the left and on the right of this picture about how we compute our standard error, standard deviation, margin of error, and now all the computations move to the right side. So the picture is much cleaner. You don't need to do two computations. And you don't see any more overlaps of the confidence intervals. You see only one confidence interval around our test version and no intervals around control version. That's exactly the idea of why we need this change from absolute scale to the differential scale. So you're just forgetting about what the CTR means, or the absolute value of CTR. You care more about how this CTR change in case of your experiment, or is it change at all? And it is very easy to say that, okay, if this confidence interval cross the zero, it means that you can't say for sure that your results are improve the situation enough. It is better to repeat the test and get your confidence to the right of the zero, because it is still in terms of statistics, it is still not statistically significant. It is still neutral results. Okay, thank you. So let's wrap up for today, and let me introduce how much terms actually we covered in this presentation. I try to make it as small as possible, but yeah, still enough. So we touched all these terms in today. Of course, there are many more nuances in all the presentation or in all the experimentation. This just should give you some basic ability to talk with data scientists or statisticians in a bit common language, maybe with just usage of some terms. Please don't try to argue with them, because they are, of course, ended a lot of courses and it's harder to justify, but it's much easier to understand them. Actually, it would be great if you dive a bit deeper, because we know the terms right now, to learn about at least representativeness of the result and minimum detectable effect. Yeah, and in case I will able to collect the second part of this talk, and yeah, of course, if it will be requested, I can try to highlight these areas, because I think it's the next step in your way or to the statistics and A/B experimentation. So I do not put any links in particular, because I think all the information can be easily Googled. Just put this term and Google will show you everything about it. But it just maybe not combined in this way. And yeah, thank you all. And here's my email. If you have further questions, I'm happy to answer them. Yeah, sorry, I can't do Q&A after all. So yeah, it's not possible for today. But yeah, please just mail. And yeah, this presentation will be in recording in several days. So thanks everyone. Thank you for joining, and have a nice day.